Okay, so let X be a cofinite topological space. If a subset A of the space X is closed, then either the set A is the entire set, or the set A is finite. So proof: suppose that the subset A of the space X is closed, then the complement of the set A is open. So either the complement of the set A is the empty set, or the complement of the complement of A is finite. That is, either A is the entire set, in which case the complement is the empty set, or the complement of A, which is the set A, is finite. So again, let X be a cofinite topological space. And a subset, a proper subset of the space X is closed if and only if that proper subset is finite. So proof: suppose that the proper subset A of the space X is closed, then, by the previous example, the set A is finite. So conversely, suppose that the proper subset of the space X is finite, and since the set A is the complement of the complement of the set A, and once again is finite, the complement of A is open, and hence the set A itself is closed. So now let X be a cofinite topological space. Where the underlying set is not finite. The only finite set which is open is the empty set, and the only infinite set that is closed is the entire set. So let the subset F of the space X be finite. let the proper subset U of the space X be infinite, then we look at the interior enclosure of some subsets in this cofinite topological space on a underlying set that is not finite. So the empty set is its own interior and its own closure. A finite set is its own closure, and the only open set contained in the finite set is the empty set. The infinite proper subset of the space X is an open set, so it is its own interior. And the only closed set which contains an infinite subset is the entire set. And so, of course, the entire set is its own interior and its own closure. But notice in particular that the closure of any infinite set in a cofinite topological space is the entire set. So since the empty set and the entire set are the only sets which are both open and closed, the space X is connected and since the closure of a infinite set U is the entire set, and I'll state that explicitly, where the proper subset U of X is infinite, we have that every infinite subset U of X is dense in the space, and since there exists a countably infinite subset, which we'll call D of X, this set is dense and countable, and so the space X is separable. So we can summarize some of the topological invariants for a cofinite topological space where the underlying set is not finite. So in this case, the number of isolated points is 0. The strongest separation condition satisfied is the T1 condition, or the Fréchet condition. A cofinite topological space on a non-finite set is connected. And one of the countability conditions satisfied is that it is separable. So as an exercise, let X be a cofinite topological space. Show that every finite set is nowhere dense in the space X. Okay, So recall that a set A is countably infinite if and only if there exists a bijection which we'll call phi, mapping the set into the set of positive integers. So evidently, the set of positive integers is itself a countably infinite set. Since the identity map on the set of positive integers is a bijection. Okay, so next we will prove a lemma. Every infinite subset of the set of positive integers is countably infinite So proof. Let the set C be an infinite subset of the set of positive integers. We will construct a map from the positive integers into the set C by induction. So define the function h, mapping the positive integers into the set C by first stating that the element 1 in the set of positive integers is mapped onto the smallest element in the set C. Notice that H1 is uniquely defined since the subset C of the positive integers together with a relation less than or equal to or is bounded below by the number 1 in the set of positive integers. And so there is a least element or a smallest element in a subset of the positive integers, and the number 1 in the set of positive integers is mapped onto the smallest element that is in that set, and this is a one-to-one map. That is, the element is mapped to exactly one element. So assume that h sub 2 or h of 2 through h of n minus 1 are defined. So this is the induction hypothesis. Then h of n is the smallest element, and the complement of the direct image of the set of positive integers from 1 to n minus 1 Now notice that this complement is not empty, since otherwise the map from this set of positive integers from 1 to n minus 1 into the set C is a surjection Therefore, the set C is finite. So, by induction, the function h is defined for every positive integer n, and thus the function h is a function from the set of positive integers into the set C. So a function exists. We now must show that this function is a bijection, or rather that there exists a bijection mapping the set C into the set of positive integers. So first we'll work with this map and show that it is a bijection. So suppose that m is not equal to n. Without loss of generality, we may assume that m is less than n. Notice that h of m is in the direct image of the set of positive integers from 1 to n minus 1, while h of n is not in this set. H of m is in this set. H of n is not in this set. Since by definition it is in the complement of this set, it is the smallest element in the complement of this set in the set C. And so h of m is not equal to h of n, and so the assumption that m is not equal to n leads to the conclusion that h of m is not equal to h of n. And so the function h is injective. Now, let C be an element in the set C. Notice that the direct image of the entire set of positive integers is not contained in a finite subset of the positive integers beginning with 1 and ending with C, since the set of positive integers is infinite. And so there exists a positive integer n such that h of n is greater than C. So let m be the smallest positive integer such that h of m is greater than or equal to C. Then, for every positive integer I less than m, h of I is less than C. And so the number C, or the element C in the set C, is not contained in the direct image of the set of positive integers beginning with 1 and ending with m minus 1. And since h of m is the smallest element in the complement of this set, we must have that h of m is less than or equal to C. That is, h of m is less than or equal to C, which in turn is less than or equal to h of m. And so we have trapped the value of C between h of m. And so h of m is equal to C. And so the function h is surjective, since for each element C in the set C there exists a positive integer m such that h of m is the element C. So as the function h is both injective and surjective, the function h, which again is a map from the set of positive integers into the set C, is a bijection. And so the inverse exists, and this is a map from the set C into the set of positive integers, and this is also a bijection. And therefore, the set C is countably infinite.